Alright, now I will show you how to use Matlab for this assignment about the pad bearing and how to solve Reynolds equation numerically. First of all, you open up Matlab, then you will see something like this. After that, we open up the file, which is the pad1d file. It should be here somewhere. Alright, so this is the Matlab script. It's not a very long Matlab program. It's and if you haven't been using Matlab at all, you maybe need some knowledge about programming, like in Fortran or Visual Basic or C++ or similar. But pretty straightforward. You really need to learn Matlab if you haven't already. You can see here the starts up here, and there are not that many lines in this program. We start with entering some input data, the length of the bearing, the width of the bearing, the viscosity, the speed. And here I define the grid. You remember in the finite difference method you need a grid. And here I choose 200 grid points. You can choose any number. You don't need that much, or in some cases you need much more. Here I define the actual length of each element, and here I define a vector or an array with x positions of each grid point. This is the constant, the input of the tilt angle, the tilt of the bearing. You see here that it's in radians. Everything is in radians in SI units, and it's a very small number. You can see it's. Here I give a number of the minimum film thickness, and here I define the single wedge. So here I define a vector or an array h as h minimum plus theta multiplied by L minus the x vector. So this becomes an array in itself, and it describes the film thickness in each grid point. Here I have some extra code for the double wedge also. You can use them if you wish, but in this case we want to run the single wedge, so I just add the percent sign here, and the percent sign is a comment line. So that means that lines beginning with a percentage sign is not executed at all. And here you have some extra code for a step bearing. You can open them up if you wish, if you want to use that. Then next step is to define the A matrix. So the code starting here, ending here, is to define the coefficient matrix A. You can see the slides for what that is, and then also the right hand side, I believe it's called F in the slides. Here it's it's a derivative of h, so it's dh dx more or less, but in numeric form here. And here I define an empty vector p, and I know that the inlet pressure is 0 in this case, and its outlet pressure is also 0. And then I actually solve the system of equations by using Gauss elimination, simply by using a \RHS. So this is an operator in Matlab that helps us to solve equation system of that kind. Next step is to compute the load carrying capacity, and that's just a numerical integral of the pressure. And you may also compute the shear stress if you wish. And finally here it's some plotting of P versus X. So it's very easy. When you want to execute this, you may press run here. And then normally your file is in another folder, so you just press change folder here, and then the program was executing, and here is the plot of pressure versus x direction. And you can see here that the pressure increases, reaches a maximum somewhere in the middle, in the more towards the right end or towards the outlet, and then it goes down to 0 again. So this is the numerical solution and the way of using Matlab. Now you can run this from this command window also. So if if I change anything, I can, well, the command window, I can use the command window also directly if I wish. If I can do, if you haven't been using Matlab, you can play around with it. You can just call something A equals 2, for example, and B equals 3. Then A multiplied by B is 6, of course. You may say that, well, you can use anything sinus A, and you can do more or less any mathematical operation in Matlab. So if you haven't learned Matlab before, please try to do that. If I go back to the editor here, this is the editor window, then you can play around with this program also. You can change, as I said, you can change the minimum film thickness and see what's happening with the load carrying capacity. You saw here that the load carrying capacity was computed. So if I, for example, increase the minimum film thickness now and run again, then as you can see that the load carrying capacity is now 3.5 meganewton per meter in this case, but it was 16 meganewton per meter in the previous case when the film thickness was smaller. So it's pretty easy to use, so good luck.